Hi guys, we're back with another video. So we're doing invert binary tree. So given the root of a binary tree, they want us to invert the tree and return its root. So given example 1, which is this tree, they want us to return this tree. And basically the only difference is that in each layer, the order of the nodes are reversed. So in this one we have 2, 7, and in this one we have 7, 2, 1, 3, 6, 9 in this one, and then it gets completely reversed, so 9, 6, 3, 1. In example 2, we have this tree to start with, and we would return this tree. So basically, this 1 and 3 swap places, and it becomes 3, 1. In example 3, we have an empty tree, so we would return an empty tree back because there's nothing to swap, right? So, I guess 3 would be our base case, right? If we're given an empty tree, which is null as the root, then we would return null back. Otherwise, so let's look at example 2 because that's the next most simple example we have. So we're just swapping the left and right children of each node, right? So if we have 2 as our root, then basically our left child, which is 1, and our right child, which is 3, swap places. So then 3 would become the left child and 1 becomes the right child. And if we take a look at example 1, on a basic level, that is also what is happening here as well. So if we really zoom in, right? So let's say node 2 is our, I guess actually example 2 is literally just this left subtree of example 1, right? Because basically we have 2 as our root, in this case, if we're just looking at the left subtree. 1 is the left child, 3 is the right child, and 1 and 3 swap places, right? As we can see here, 2 becomes the right subtree, but ignore that, right? If we're just looking at this, 3 becomes the left child, 1 becomes the right child. Then if we zoom out a little bit and we're looking at this tree with 4, 2, and 7, then the 2 and 7 swap places. So 2, which was the left child, becomes the right child in this tree. 7, which was the right child in this tree, becomes the left child in this tree, right? And then if we just look at the right subtree of example 1, then 6, which was the left child, becomes the right child of 7, and 9, which was the right child of 7, becomes the left child of 7. So every single node is just swapping places, basically. So if it was the left child, it's becoming the right child. If it was the right child, it's becoming the left child. And that's basically it. So let's start with our base case. So if our root is null, then we'll just return null. So if root is null, return null. Pretty simple. Okay, and then we will assign a tree node variable, a temporary variable, to our left and right nodes of our recursive call so that we don't lose the value. So let's say tree node left is invert tree, and then we'll just say call root.left, and then right is invert tree root.right, and then we're going to swap these values. So then root.left will become right, and root.right will become left. And then at the end, we're just going to return the root. Because this is going to, after we swap all the values, then this will be the new tree, and then our root will have stayed the same, so we'll just return the root. So that should be pretty straightforward. All right, so our time complexity, right? If we think about this, we are just doing a DFS, a pretty simple DFS actually, where we're just visiting every node once, and we swap the nodes, we swap the nodes, so the left becomes right, right becomes the left. And so when we visit every single node, that is going to be O of n, where n is the number of nodes in the tree, because we're visiting every node exactly one time. And swapping them is basically negligible. So then our time complexity will end up as O of n, where n is the number of nodes in the tree. And then our space complexity, so if we think about this, right, we don't have any additional data structures here, but we just have the call stack from performing our DFS. And so our call stack, worst case, if we have a unbalanced tree where every node is, so basically where every single node only has a left child or every single node only has a right child, so it becomes a straight line, just like a linked list or something, then our space complexity will store every single node that's in the tree. But like basically normally it's just going to be, we could say O of H, where H is the height of the tree, or O of N, where N is number of nodes in the tree. So, and this is because, so if we think about that, so because the DFS is going to explore one path as deep as possible before popping things off of the stack again, right? And so the depth is, at any point, it's going to be, the depth of any path is going to be like the height of the tree, right? But again, so if we have like a linked list type of tree, then that is going to be all of the nodes in the tree, which is O of N. But even normally, like O of H, like the height is proportional to the number of nodes in the tree, so it really doesn't matter, like it's still going to be O of N. So that is it for this problem. Thank you guys for watching, and like and subscribe if you found it helpful. Bye!